So let us recall what we did in the previous lecture. In the previous lecture, we have discussed uniform convergence of series. Also, we have talked about uniform convergence of sequence also in the previous few lectures. We are discussing this. And we have solved certain examples based on how to test whether the given series is uniform convergence or not, whether given sequence is uniform convergence or not. So for that we have studied regarding the what are the different tests for testing a given series or sequence. The one of the test is a Verstappen test. So we have solved certain examples based on Verstappen test, which tells you that if fk is a sequence of function which is bounded by some constant sequence of numbers and this summation of mk is convergent, then summation of fk is uniformly convergent. This is known as a Verstappen test. Also, we have discussed certain things in the previous lecture that if you have given a sequence which converges to f pointwise, where each of this function fn are continuous, but it does not mean that the function f, the limit function, is continuous. So it will not guarantee that this limit function will be continuous under the pointwise convergence. That means under the pointwise convergence, continuity will not be preserved. That we have seen by example, x power n is a sequence of function. In the interval, closed interval 0 to 1, if I take, then this sequence of function x power n is converged to a discontinuous function, that is 0 and 1. It will have a 1 value if x is 1. Otherwise, that means any value is between this two, then it will be 0. This is a sequence of polynomials and it's converged to a discontinuous function. So it's concluded that under the pointwise convergence, the continuity is not preserved. So the next theorem that we are discussing in this lecture is under the uniform convergence, the continuity is preserved. So let us state what is that theorem is. So theorem, let fn be a sequence of continuous function on E, where E may be a subset of R or maybe it is a subset of C. That means as a subset of a real number or it is a subset of complex number. Converging uniformly to F on E. So this sequence of Fn is a sequence of continuous functions. Sorry. Yeah. It is a sequence of continuous function in which uniformly converges to this function F. Then prove that F is continuous on E. Ultimately, if each of this Fn is continuous and the convergence is uniform, if all of them are continuous, then F is continuous. That is the statement of this result. Ultimately, we can say that under the uniform convergence, a continuity is preserved. So let us discuss the proof of this statement. So to discuss the proof, let us take this x0 is any point in this set E. we shall show that f is continuous at point x0. So if you want to show that f is continuous at the point x0, that means for any epsilon greater than 0 be given, we have to prove that mode of f of x minus f of x0 is less than epsilon whenever mode of x minus x0 less than delta. So I have to find out such delta such that this thing is happen. So let's epsilon to be given is there, and given that this fn is uniformly convergent, also this each of fn's are continuous. So we have to use both this condition. Since the sequence fn is uniformly converges to f, therefore, or I should not say therefore, there exists n0 belongs to n such that mode of fn of x minus fx is less than epsilon. I will adjust this epsilon later on. For every n greater than or equal to n0 and for every x is belongs to E. I may call this as the statement 1. Since this fn, the sequence fn, or for all n, fn is continuous at x0. Therefore, the same delta, sorry, for same epsilon, there exists some delta greater than 0 such that mode of x minus x0 less than delta implies mode of fn of x minus fn x0 less than epsilon. This epsilon also I will adjust later on. This is, we call it statement number 2. Ultimately, I have to show that for some delta, this has to be. So I need to find out what is fx minus f, fx0. So now if we take your x minus x0 less than delta, then we have mode of f of x minus f of x0. So we have to add and subtract some terms here. So I will add fn x due to this quantity fn x minus fx plus fn x minus fn x0 to make this arrangement plus fn x0 and minus fx0. So this is by triangle inequality, we can say that it is fn x minus fx plus fn x minus fn x0. This is fn x0 minus fx0. So in the first, this modulus, we use the statement number 1, which tells you that fn x converges to f for every point in that. So this is epsilon upon 3. So I have 3 terms. That's why I'm just adjusting epsilon by 3 here. Here also epsilon by 3. In the second, this modulus, we'll use this equation or the statement 2, which tells you that fn is continuous. So plus at x0, epsilon by 3. In the last term, at the point, it is here we are actually using the pointwise conversion at the point x0. So it is a sequence of number. Due to the same statement 1, in particular for x0, this is also true. So using the statement that we can write this is less than epsilon by 3. That is equal to epsilon. Whenever we know that when mode of x minus x0 is less than delta. So hence what we can say is f is continuous on every point on E, which proves that under the uniform convergence, continuity is preserved. The question arises whether the converse is true. That means if f is continuous, can we say that a convergence is uniform? The answer to this question is no. That will not be true. So the converse of this result is not true. Let us see by an example. So let us consider this example so that fn of x is equal to n square x power n 1 minus x. X belongs to closed interval 0, 1. Converges pointwise but not uniform. But not uniformly to the function which is continuous on closed interval 0. That means we have to show that this function, sequence of function, is converse to a continuous function. But the convergence is not uniform, it is pointwise convergence. So it tells you that the converse of the above result which we discussed is not true. So let us have the proof or a solution for this problem. Here what is given, your x is between 0 and 1. So I just take it is in open interval 0 and 1. Since it is in open interval 0 and 1, 1 minus x is between 0 and 1. So if I multiply minus sign both sides, we have this, and if I add 1 both sides, then this is 1 minus x is between 0 and 1. So this is the bounded thing, n square into x power n. Your x is between minus 1 and 1, so therefore, and limit of n tends to infinity, x power n is 0 as your x is between 0 and 1. So ultimately what we can say, this quantity, that is fn of x, is n square x power n 1 minus x is tends to 0 where when x is between 0 and 1. Now what will happen at 0? What is f of fn at 0? This is your fn. The value of fn is x is equal to 0 is there. If you substitute, and this will be 0. And fn at 1 is also 0 because x is equal to 1 will gives you 0. So hence what we can say, fn of x, which is n square x raised to n 1 minus x, converts to pointwise to 0 function as n tends to infinity. Here it is a 0 function, so your f, this function is your f. So we note that f equal to 0 is a continuous function. So 0 function is already continuous on closed interval 0. In fact, it is continuous on R or whatever the domain is there. In particular, it is continuous on this closed interval 0, 1. Now we have to determine whether this convergence is uniform or not. So for that, we know that we have learned one result to discuss the convergence uniformly or not. We have to see or find out what is Mn. Mn is a supremum of mod of fn of x minus fx, as your x is in a domain which is closed interval 0. If this Mn is tending to 0, then we can say that Fn is converged to F uniformly. If it is not tending to 0, then pointwise. So to calculate this one, we can say that this is supremum of n square into x power n 1 minus x minus 0. And in between 0 and 1, this quantity is always positive. So ultimately, I had to calculate what is the supremum of this function. X belongs to closed interval 0. So let us consider, to find out the supremum of this, let us consider g of x is equal to n square x power n 1 minus x. And we know that to calculate the supremum, we have to find out what are the stationary points. Stationary points means that where the g dash of x is 0. So we'll start with 0 of x. We can calculate this. There is n square x power n, as it is derivative of 1 minus x is minus 1 plus 1 minus x, as it is derivative of x power n is n into x power n minus 1. And if you can take common out x raised to n minus 1, so this is n square x raised to n minus 1. This will gives you minus x plus 1 minus nx. Now g dash of x equal to 0 will gives you n square will never be 0. So this is gives you x power n minus 1 is 0, or 1 minus 1 plus n x is equal to 0. That is come from this. So this will imply x is 0 or x is equal to 1 upon 1 plus 1 upon 1 plus n. Now, oh yeah, here this is n, this n should be multiplied to 1, so this is n. Yeah, so this n is there. So n upon 1 plus n is there. So I forgot. So that is g double dash of x. That is the derivative of this quantity, n square as it is, x power n minus 1 as it is. The derivative of this quantity is minus 1 minus n plus n minus x minus nx as it is. That is this term as it is. A derivative of x power n minus 1 is n minus 1 power x raised to n minus 2. Now if I put x is equal to 0 and this value here, obviously when x is 0, this is 0, this will be 0. So we note that g double dash of 0 is 0. And g double dash at this n upon 1 plus n. We can substitute that value here. And this term will tend to 0 if I have x is this, because that is actually roots of this equation. So this term is 0, so you'll have this term. And if I take minus sign out, that is n square into 1 plus n and n upon 1 plus n power n minus 1. This is the term, and this is negative. Since this will be negative, This n upon 1 plus n is the maxima of the function g. So therefore x is equal to n upon 1 plus n is maxima of g. Therefore mn is equal to supremum of mode of fn of x minus fx as your x is belongs to close interval 0 1 will be g of n upon 1 plus n. Now what is the function g that we have defined as this n square into x power n 1 minus x. This is your function g. Now if you substitute x is equal to n upon 1 plus n here. So this is n square into n upon 1 plus n power n into 1 minus n upon 1 plus n. Now let us see what is this quantity. This is n square, and if you take the LCM here on this side, that is in this bracket, that is n plus 1 minus n upon n plus 1. N is get cancelled out, so it is n square upon 1 plus n. And this is n upon 1 plus n whole raised to n. So this will be gives you n upon 1 plus 1 by n. If I divide by n in the numerator and the denominator, we'll have this. And this quantity also I can write 1 upon 1 plus 1 by n whole power n. Here I have a divide by n power n into numerator and the denominator. So that's why we have this. And we know that the limit of x tends to 0. 1 plus x power 1 upon x is e. So as per this quantity which we have here, which is tending to e, this will tends to 1 and this is tends to infinity. So this I can say it will tends to infinitive as n tends to infinity. So finally what we can say is this mn is tending to infinity, which is not equal to 0. So therefore mn is not tending to 0 as n tends to infinity. Therefore fn is not converge to f. It is converge to but not uniformly. Fn will not converge to f uniformly. That we can say. So I should write Fn is not uniformly converge to F. Okay. So this theorem or this example tells you the converse of the above result is not true. But the negation of the result is true. What is the negation of the result? If Fn is converge to F, this is the statement, Fn is converge to F uniformly, each Fn's are continuous, which implies F is continuous. The negation of this result is that means F is discontinuous. If the function f is not continuous, that means it is discontinuous function. Then f1 will never converge uniformly to f. Okay, it always converges pointwise. So if f is discontinuous function, then definitely without calculating you can say that fn converges to f not uniform. It should converge pointwise only, should not converge uniformly. That is the negation of this result. So whenever this is another way to deal with the uniform convergence of sequence, if your limit function is discontinuous, definitely that convergence is not uniform. That is a conclusion we can make out of this. Let us have one examples based on a continuity of the function as a series. So prove that the series summation n running from 0 to infinity x power n upon n factorial. This is very well known series of e power x is converged to a continuous function on the interval I. We know that this is an expansion of e power x. Here our objective is to prove that this function or this series is converged to some continuous function. So if you want to prove that this series is converged to some continuous function, you have to prove that this series is uniformly convergent, because each of this term x power n upon n factorial is continuous, because it is a polynomial kind of functions are there. So once I can prove that this series is uniformly convergent, then we are through. So to prove that is uniformly convergent, we have to use the Weierstrass M test to prove the series is uniformly convergent. So for that, first I will prove this series is pointwise convergent. That can be proved by ratio test, because this is x power n upon n factorial. Or you can say this is a power series. So in it, whatever the domain is there, so here the series summation x raised to n upon n factorial is converged pointwise to the sum function fx on R. Why? Because by ratio test, an plus 1 upon an. What is an? Is x power n upon n factorial. So an plus 1 is x power n plus 1 upon n plus 1 factorial. And an is x power n upon n factorial. So n factorial I can write down here. So this will gives you x upon n plus 1. And we know that this will tends to 0 as n tends to infinity, which is less than 1. So for any x belongs to R, this series is convergent. So it is a pointwise convergence. What we have to prove, this series is uniformly convergent. So for that I need to prove that it is by Weierstrass M test. So it has to be bounded by some constant sequence. So we'll prove this. What to show is this: the given series converge uniformly to the function fx on the interval minus m to n for every m greater than 0. So for any m, I may take this interval. So we note this thing that mode of x power n upon n factorial is always less than or equal to m raised to n upon n factorial for on this interval minus m to n. And the m power m upon n factorial is always a convergence by ratio test. So by ratio test, we say that summation m raised to n upon n factorial is convergent. Therefore, by Vasta's M test. We say that summation x raised to n upon n factorial is uniformly converged on minus m to n on this interval. And so by above results which we have discussed, that under the uniform convergence the continuity is preserved because each of this x power n upon n factorial is a continuous function. So therefore we can say that f, whatever the limit to this function, so therefore by above theorem the fx is continuous on closed interval minus n to m. But here I have taken this m is arbitrary number. I have taken m, there is no restriction on m is there. So but m greater than 0 is arbitrary. So I can say that this function f is continuous on any value in R. And this completes the solution for this example also, which tells you that under the uniform convergence of a series, the limit function is also continuous, or by proving that the limit of this function, this sequence of function is continuous. If you have any question, you can ask till now.